What you're looking at is a complete solar power plant: panels, battery storage, power electronics, and a grid connection, built entirely inside Simulink. No physical hardware, no lab bench. Every volt, every amp, every switching pulse in this system is computed, block by block, in software. By the end of this video, you'll understand exactly how power flows from sunlight all the way to a real AC load. And in the rest of the series, we'll go inside every single block to see exactly how it works. Here's the challenge this model is solving. Solar panels don't produce power on demand. Output swings with sunlight and temperature, and it can drop to zero the moment a cloud rolls over. But a load, a house, a factory, a section of the grid, needs power continuously, regardless of what the sun is doing. So this system does three things at once. It squeezes the maximum possible power out of the panels at every instant. It uses a battery to store surplus power and cover shortfalls, and it delivers everything to the load as clean, usable three-phase AC. Let's trace how. Start at the source. This blue block is the PV array, a full mathematical model of a solar panel, built from the single diode equation you'll find in every solar physics textbook. Feed it sunlight and temperature, and it outputs current and voltage exactly like a real panel would. But a solar panel only produces its maximum power at one specific voltage, and that voltage constantly drifts as conditions change. So right next to the panel sits the MPPT algorithm, maximum power point tracking. Every few microseconds, it nudges the panel's operating voltage up or down and watches what happens to power, homing in on the peak in real time. That target voltage gets enforced by the boost converter, a switching circuit that physically forces the panel to operate at exactly the voltage the MPPT wants, while stepping that voltage up to a higher DC bus level the rest of the system can use. Now, here's where it gets interesting. That DC bus doesn't just go straight to a load. It connects to a battery through its own bidirectional converter. And deciding what that battery should do at any given moment is the job of the energy management system, constantly comparing how much the panels are producing against how much the load needs, and checking the battery's state of charge before deciding charge, discharge, or hold steady. Whatever that decision is, it gets executed by two power switches, IGBT1 and IGBT2, forming a half-bridge that can push power into the battery or pull power out of it on command in real time. Finally, all of that combined DC power, from the panels and the battery together, reaches the inverter. This is the stage that converts direct current into the three-phase alternating current that an actual grid or AC load needs. A voltage control loop inside the inverter keeps that output locked to the correct amplitude and frequency, and a final measurement block continuously reports back the real and reactive power being delivered. That's the full journey: sunlight in, usable AC power out, and every single stage in that chain is its own small engineering problem, solved with real equations and real control theory. In this series, we're going inside every one of those blocks. We'll look at the exact diode equations behind the solar panel, the logic behind the MPPT algorithm, how the boost converter switch actually creates a voltage boost, how the energy management system makes its charge and discharge decisions, how the battery's own discharge characteristics are modeled, and how the inverter locks onto the grid and controls its output voltage. If you want to jump straight to any of those topics, check the cards and description below. Otherwise, stick around. We're about to open up the first block. Let's start where the power itself starts, right here, at the solar panel. This blue box is the entire solar panel in this simulation. 3 inputs: voltage, irradiance, temperature, 2 outputs, plus and minus terminals. That's it. But under the hood, it's running the exact physics of a real PV module. 2 MATLAB functions computing photocurrent and diode current, wired into an actual electrical circuit. In this video, we're opening up the PVG subsystem and walking through both functions line by line, so you know exactly what's happening every time this block runs. Let's dive in. Outside, the PVG block takes 3 signals. VPV, the operating voltage across the panel, fed back from the circuit it's connected to. G, irradiance, set here to a constant 1000, which is standard test condition sunlight in watts per square meter. T, temperature, set to 298 Kelvin or 25 degrees Celsius, the standard reference temperature. And it outputs two physical terminals, plus and minus, that you'd wire up just like a real solar panel in your circuit. Double-click that block, and this is what's actually running inside. Two FCN blocks, one labeled IF, one just labeled FCN for diode current, a sum block, a controlled current source, a series resistance, and a current sensor feeding back into the diode calculation. Let's take these one at a time. This first function computes IF, the photocurrent, meaning the raw current generated directly by sunlight hitting the cell before any losses. Two inputs, T, temperature, and W, which is irradiance, wired from the G input on the outer mask. There are two terms being added together. First, temp term, a temperature correction. Alpha, 0.0022, is a linear temperature coefficient. For every degree above the 298 Kelvin reference, photocurrent nudges up slightly. That's a real physical effect. Solar cells actually produce marginally more current, though less voltage as they heat up. Second, term, the irradiance term. ISC 3.87 is the short-circuit current rating of a single-cell string, scaled down by scale, 1,000th, and multiplied directly by irradiance W. More sunlight in, more current out, a straightforward linear relationship. Add those two terms, multiply by NP1, 6, the number of parallel strings in this array, and that's your total array photocurrent. At standard conditions, 1000 W/M superscript 2 and 298 K, that temperature term drops to 0, and you're left with IPH is equal to 6 times 3.87 times 0.001 asterisk 1000, which comes out to about 23.2 amps. That's your array's rated short-circuit current under full sun. The second function is where most of the real physics lives. It computes ID, the diode current lost internally to the PN junction of the cell, and it does it in two clearly separated stages, each its own subfunction. Notice the inputs here. T for temperature, I, and this is important, is fed back from the current sensor later in the circuit, and V is the panel voltage, VPV, from the mask. Z is hard-coded as 72, the number of cells wired in series in one string. This function just orchestrates two steps. First, compute I0, the diode's saturation current at the current temperature. Then, use that I0 to compute the actual diode current, ID. This is two calculations back-to-back. First, I0_T1, the saturation current at the reference temperature, 298 Kelvin. It's derived directly from the panel's rated open circuit voltage, VCO, 42.1 volts, using the diode equation evaluated at the point where current is 0. That's the physical definition of open circuit voltage. Then, the function scales that reference value up or down for the actual operating temperature T, using two correction factors, a power law ratio term, T/T1, raised to 3/1.397, and an exponential term built from the bandgap energy Eg. That Eg value being negative here is deliberate. It reflects how the bandgap term interacts with the exponential to correctly increase saturation current at higher temperatures. This is the same effect that makes semiconductors leakier when they're hot. Compute_ID1, the diode equation itself. This is the classic single diode current equation, scaled up for the full array. Z1 72 times 6 times 8 and Z2 72 times 8 account for the full cell count across all series and parallel strings and modules in the array. NP and NP1 scale for parallel strings, and RS 0.0071 ohms is the series resistance of the array. Plug in I0 from the previous stage, the measured voltage V and current I, and out comes the diode current, the current the array loses internally, which gets subtracted from the photocurrent to give you the panel's real output. Now watch how these two functions plug into the physical circuit. If and ID both feed into a sum block, if minus ID. That's the net current the array should be producing right now, given the current sunlight, temperature, and operating point. That net current drives a controlled current source, the circle with the arrow, labeled ID1. This is a Simulink block. It takes your calculated number and turns it into an actual current flowing through the circuit. That current passes through a series resistance, the zigzag, which is the physical resistance term, RS, showing up again here as an actual electrical component causing a voltage drop. And right after that resistor sits a current sensor. It measures the real current flowing through the circuit and feeds it straight back into the ID function as the I input. That feedback loop is the key detail. The diode current depends on the actual circuit current, and the actual circuit current depends on the diode current. It's a closed algebraic loop, exactly how a real solar cell behaves, where voltage and current are locked together by the physics, not computed once and forgotten. So to summarize, this innocent-looking blue box is running the full single-diode solar cell model, photocurrent from one function, temperature-corrected diode current from another, combined through a real current source and series resistance, with a feedback loop closing the physics. Change G and T on the mask, and you're simulating your panel under any sunlight and temperature condition you want. That's what makes this block reusable everywhere in the larger system, the boost converter, the MPPT controller, the whole microgrid, because the physics is fully self-contained right here. Prioritize clarity over technical jargon for accessible explanation. This is the perturb and observe, PNO, and MPPT algorithm, implemented as a discrete MATLAB function block. It's the same logic as the diagram you showed earlier, just written directly in code instead of built from 1/Z delay blocks and logic gates. Persistent state, memory across time steps. Since this function runs once per simulation time step, it needs to remember values from the previous step to compute a derivative. Persistent variables do exactly that. They behave like unit delay 1/Z registers. P_prev power from the last step. VZ1, VZ2 voltage delayed by 1 and 2 steps. This double delay is what avoids the algebraic loop you'd get from feeding V straight back into its own derivative. VPV_prev the last commanded voltage. This is what makes the output an integrator. Each step nudges away from wherever it left off. Init a one-time flag, so these all get reset to 0 exactly once, on the very first call. The core calculation. P is instantaneous power from the current measured voltage and current. dP is the change in power since the last step. dV is the change in voltage, but computed from the delayed values VZ1, VZ2, not the current one, again to prevent a circular dependency. The decision logic. This is the classic PNO rule, written as arithmetic instead of if/else. If dP and dV have the same sign, XOR_val equals 0, power and voltage move together. You're still climbing toward the peak, keep stepping the same direction, plus d step. If they have opposite signs, XOR_val equals 1, you overshot the maximum power point reverse direction, minus d step. Gated_step zeros the step out entirely if dP equals 0. No change in power means no reason to perturb. Updating the voltage command. The new reference voltage is just the old one plus or minus the tiny step. This is what makes it perturb. Nudge the operating point slightly and see what happens next time. Saving state for the next call. In short, every time step, this function asks, did nudging the voltage last time increase power? If yes, nudge the same way again. If no, nudge the other way. Over many steps, this hunts the panel's voltage toward whatever point maximizes power output, automatically adapting as sunlight or temperature changes. PWM generator. This is the PWM generator for the boost converter. It takes the MPPT's voltage reference and translates it into an actual switching signal for the IGBT/MOSFET in the boost converter. Signal trace. 1. Error calculation. Error equals VPV minus ref1. A VPV, port 1 the actual measured panel voltage. Ref1, port 2 the target voltage commanded by the MPPT, perturb and observe algorithm. The sum block computes the voltage error, how far the panel currently is from its commanded operating point. The PID controller. This is a discrete PID controller block. It takes the voltage error and computes a control effort. This is the classic feedback control law, proportional, integral, and derivative terms acting on the error. Driving the duty cycle command toward whatever value makes VPV track for F1. 3. Saturation block. The diagonal line block right after the PID clips the controller's output to a fixed range, almost always 0 to 1 in a duty cycle context. This prevents the PID from commanding an invalid or unsafe duty cycle, like negative or above 100%, which is essential since integral action can otherwise wind up beyond physical limits. 4. Carrier wave generator, sawtooth/triangle block. The block with the repeating ramp/triangle waveform is a fixed-frequency carrier signal, a sawtooth or triangle, wave oscillating between 0 and 1 at the switching frequency of the converter, e.g., 10 kHz, 20 kHz, whatever the model specifies. 5. Comparator, greater than or equal to. This is the actual PWM modulator. It compares the saturated duty cycle command against the sawtooth carrier. PWM equals 1 if duty_CMD greater than or equal to carrier. PWM equals 0 otherwise. This subsystem is the decision maker for the entire battery in this microgrid. 4 inputs come in: battery power, load, PV generation, state of charge, and 2 switching signals come out, driving IGBT1 and IGBT2 directly. In between, there's a MATLAB function making a genuinely complicated decision: should the battery charge, discharge, hold, or protect itself, followed by a PI controller and a PWM generator that turns that decision into an actual gate signal. Let's open it up and go through it end to end. Here's the flow at a glance. Pload, PPV, and SOC all feed into an FCN block that outputs ref, the reference power the battery should be delivering right now. That reference gets compared against PB, the actual measured battery power, producing an error. A PI controller acts on that error, gets clipped by a saturation block, and finally gets compared against a sawtooth carrier to produce a switching pulse train, PWM for 1 IGBT, and its logical inverse, PWM1, for the complementary IGBT. So really, this is 2 separate jobs stacked together. First, decide how much power the battery should move. That's the FCN block. Second, make it happen electrically. That's the PI plus PWM stage. Let's start with the decision-making. 1. Deficit. Pload greater than PPV, then battery should discharge. 2. Excess. PPV greater than P load, then battery should charge. 3. Meet. PPV equal Pload, then hold. No action needed. 4. SOC limit reached, then override with a safety reference. The function's whole job is figuring out which of these situations is true right now and computing the correct pref value for it, all while respecting the battery's SOC limits and power rating. Let's dig into the code. First thing, a persistent variable, pref_prev. This is the code equivalent of that vertical integrator loop you can see feeding back into the diagram. Its whole purpose is for the meet case, when load exactly equals generation. Instead of forcing the battery to some arbitrary value, the function just holds onto whatever pref it computed last time. It's memory across time steps, just like the persistent variables we saw in the MPPT function. This sets up every Boolean the function will need. PNet is the power balance. Positive means surplus PV. Negative means shortfall. Is deficit, is excess, and is meet are mutually exclusive. Only one is ever true. And can discharge/can charge are the SOC guardrails. Don't discharge below 20%. Don't charge above 80%, protecting the battery's health. Everything from here on is just combining these Booleans correctly. When there's a deficit and the battery's allowed to discharge, there are actually 2 subcases here, mirroring the 2 end gates you'd see stacked in the block diagram. First subcase, the shortfall is smaller than the battery's power rating, Pmax, 3000 watts. In that case, just discharge exactly enough to cover the shortfall. Term 1 equals PNet_abs. Second subcase, the shortfall is larger than what the battery can supply. In that case, cap it, discharge at the maximum rate, Pmax, rather than trying to cover a deficit the battery physically can't handle. Notice the second if block overwrites term 1 rather than adding to it. In the actual diagram, these 2 conditions are mutually exclusive AND gates feeding into the same summing junction, so only one of them is ever non-zero at a time. The code is just written sequentially instead of as parallel logic paths. This is the simplest branch. If load exactly matches generation, don't compute anything new, just output whatever PB_ref was last time. This is exactly what that persistent variable from earlier was for. It prevents the battery from jumping to zero the instant supply and demand balance out, which would cause an unnecessary power transient. Mirror logic to the deficit branch, but for charging. Both subcases here actually compute the same value, P_abs, the magnitude of the surplus power, but under different SOC conditions. Worth flagging. In this particular version of the code, neither branch caps at max the way the deficit branch's second case does. That's a subtle asymmetry worth double-checking against your actual diagram if the battery is ever charging faster than its rating allows. This is the safety net. If there's a deficit, but the battery's SOC has already dropped to 20% or below, can discharge is false. The function doesn't try to discharge further. Instead, it assigns a fixed fallback value, ref_neg, negative 800 watts. The second half checks a similar condition on the charging side and can add another ref_neg on top if that condition is also true, though in practice, only one SOC limit condition should ever be active at once, since deficit and excess are mutually exclusive. This whole term then gets multiplied by -1 at the very end, which is why the constant is written as a negative number now. The final sign flip in the summation restores it to the intended safety override direction. All four terms get added together into one final summing junction, exactly matching that big summation node you can see in the block diagram. Because the four operating conditions are mutually exclusive, only one term is ever non-zero at any given instant. The rest are all zero, so this sum always resolves to exactly the right branch's value. The result gets saved as PB_ref_prev for next time, and output as PB_ref. That's the full energy management decision, made fresh every single time step. So now we have PB_ref, but a number alone doesn't switch anything. The rest of the diagram turns it into real gate signals. First, PB_ref is compared against PB, the actual measured battery power, producing an error. That error drives a PI controller, proportional plus integral, which continuously adjusts its output to drive that error towards zero. This is standard closed-loop power control. The PI doesn't care why the battery should deliver a certain power, it just works to make the measured power match the commanded one. The PI's output passes through a saturation block, clamping the duty cycle command to a valid range. Again, protecting against integrator wind-up driving an invalid or unsafe duty cycle. That clamp signal is compared against a sawtooth carrier wave using the greater than or equal to block, the same naturally sampled PWM technique from the boost converter's PWM generator. Every time the carrier ramps past the duty cycle value, the output flips, producing a switching pulse train. This is PWM driving IGBT1. And finally, that PWM signal passes through a NOT gate to produce PWM1, the exact logical inverse, driving IGBT2. This guarantees the two switches in the half-bridge are always in complementary states. When one is on, the other is off, which is exactly the behavior a half-bridge needs to avoid shorting the DC bus. This dialog box is where you tell Simulink exactly what battery you're simulating, not just a generic voltage source, but a real electrochemical model with capacity, internal resistance, and a discharge curve that actually sags the way a real battery does under load. In this video, we're going through every single parameter in this lithium-ion battery block, what it means physically, and how it connects to the discharge curves you see plotted on the right. Let's go. Let's start with the main parameters tab. First, type, lithium-ion. Simulink's battery block supports a few chemistries: lead, acid, nickel-cadmium, nickel metal hydride, lithium-ion, and each one uses a slightly different discharge curve shape internally. Lithium-ion is what most modern battery energy storage systems actually use, so that's the right choice here.
Nominal voltage equals 13, 2 multiplied by 8 rovnítko 105, 6 volts.
This field is written as 13.2 multiplied by 8 rather than a single number, and that's deliberate. 13.2 volts is the nominal voltage of one battery module, and 8 is the number of those modules wired in series. Multiplying it out gives the actual pack voltage, 105.6 volts, but keeping the expression in this form makes it immediately clear how the pack is built. 8 modules in series, each rated around 13.2 volts, which is a very standard rating for a 4-cell Li-ion module. Rated capacity equals 35 multiplied by 2 is equal to 70 Same idea here. 35 amp-hours is the rating of a single string, and 2 is the number of strings connected in parallel. Two 35 amp-hour strings in parallel gives a total pack capacity of 70 amp-hours, and you'll see that number, 70, show up again in a moment on the Discharge tab as maximum capacity. Writing capacity and voltage this way, as multiplication expressions instead of flat numbers, is a great habit, by the way. It documents your actual pack architecture directly in the model, so anyone opening this file later can immediately see its 8 modules in series, 2 strings in parallel, without digging through datasheets. Initial state of charge, % equals 55. Battery response time, S, equals 30. Initial SOC, 55%, just sets where the simulation starts. The battery begins the simulation already half-charged, which is a common way to test both charge and discharge behavior, without waiting through a full cycle. Battery response time, 30 seconds, is a first-order filter time constant Simulink applies internally to smooth out the battery's voltage response. Real batteries don't respond to current changes instantaneously. There's some electrochemical lag. This setting tells the model how fast the internal voltage should settle after a sudden change in load. 2 checkboxes are left unticked here: simulate temperature effects and simulate aging effects. Leaving these off keeps the model simpler and faster to simulate. The battery behaves the same regardless of ambient temperature or cycle count. If you wanted to study things like capacity fade over years of cycling or reduce performance in cold weather, you'd enable these, but for a power flow and control study like this one, they're usually left off. Now the Discharge tab. This is where Simulink translates those basic specs into the actual voltage versus capacity curve you see in the plots. Notice the checkbox at the top, determined from the nominal parameters of the battery. It's checked here, which means Simulink is automatically calculating every field below: cutoff voltage, fully charged voltage, internal resistance, and so on directly from the nominal voltage and capacity we just set, using standard Li-ion characteristic ratios. That's why all these fields appear grayed out. They're computed, not manually entered. Let's go through what each of these computed values actually represents on the discharge curve. Maximum capacity, equals 70. This just matches our rated capacity from before, 70 amp-hours, the total charge the pack can hold. Cutoff voltage, V, equals 79.2. This is the minimum voltage the battery is allowed to discharge down to before it's considered fully depleted, the point where the discharge curve's steep final drop-off happens. Simulink typically sets this around 60% of nominal voltage for Li-ion, which checks out. 79.2 is roughly 75% of the 105.6 nominal, a conservative cutoff that protects the cells from deep discharge damage. Fully charged voltage, V, equals 122.917. This is the voltage the pack sits at when it's topped all the way up, higher than the nominal 105.6 volts, since Li-ion cells always read higher voltage near full charge before settling down to their nominal plateau during actual use. Nominal discharge current, A, equals 30.4348. This is the discharge rate that the nominal voltage rating is actually specified at. You'll notice the plot title says exactly this: nominal current discharge characteristic at 0.43478 C, 30.4348A. That C notation means the battery is being discharged at 0.43478 times its rated capacity per hour, a fairly moderate, realistic discharge rate for characterizing the curve. This top plot shows the full discharge curve at that nominal current, 30.4348 amps. 3 regions are color-coded. The yellow exponential zone right at the start. Voltage drops quickly as the battery transitions from its fully charged voltage down toward nominal. The gray nominal area, the long, gently sloping plateau where the battery spends most of its useful discharge life. voltage decreasing slowly and predictably. The blue discharge curve tail, the steep final drop as the battery approaches full depletion and hits the cutoff voltage. This three-region shape is the signature look of a lithium-ion discharge curve, and it's exactly what the model reproduces using the parameters we just went through. The second plot shows the same battery discharged at three different currents, 6.5 amps, 13 amps, and 32.5 amps, matching the discharge current, field back on the Parameters tab. 6.5, 13, 32.5. Notice the pattern. The higher the discharge current, the sooner the battery hits its cutoff voltage, and the more pronounced the voltage sag becomes due to that internal resistance we discussed. At 32.5 amps, the blue curve, the battery depletes in roughly 2 hours. At 6.5 amps, the yellow curve, it lasts closer to 10 to 11 hours. This is the real-world trade-off between drawing more power and getting less runtime, directly visible in the simulation. And along the top of this plot, Simulink prints out the underlying model coefficients it fit to produce these curves. E0 equals 114.5083, the fully charged open circuit voltage constant. R equals 0.015086, our internal resistance. K equals 0.011302, the polarization constant controlling the curve slope. And A equals 8.8679. B equals 0.87231, the exponential zone amplitude and time constant coefficients. These four numbers, E0, R, K, and the exponential term, are the actual mathematical parameters of the model Simulink uses under the hood. Everything we said on the parameters and discharge tabs simply gets converted into these coefficients. So to summarize, this battery block isn't just a voltage number, it's a full electrochemical discharge model. You define the pack architecture through nominal voltage and capacity, expressed here as series times parallel multiplication for clarity. Simulink then automatically derives a realistic discharge curve, cutoff voltage, fully charged voltage, internal resistance, and the exponential to nominal to cutoff curve shape, matching real lithium-ion battery behavior. And critically, this is the exact same battery whose state of charge feeds into the energy management system we covered in the last video. The SOC number driving all those charge/discharge decisions is being computed live from this discharge model, current in, current out every simulation step. This is the actual physical power circuit of a boost converter, built from real electrical components instead of math blocks. An inductor, a switch, a diode, and 2 capacitors. That's genuinely all it takes to step a lower input voltage up to a higher output voltage. In this video, we're going to trace every single component in the circuit, explain exactly what each one does, and walk through the 2 switching states that make the whole thing work. Let's get into it. On the left side, we have 2 input terminals in plus and in minus. This is where the input voltage source connects, which in this system is the solar panel and its boost stage output, or more generally, whatever direct current source is feeding this converter. Right across those 2 input terminals sits capacitor C2. This is the input filter capacitor. Its job is to smooth out any high-frequency ripple coming from the source, so the inductor downstream sees a clean, steady input voltage rather than a noisy one. Think of it as a small buffer tank that absorbs quick fluctuations before they can disturb the rest of the circuit. Next in line is the inductor, labeled L. This is the single most important component in a boost converter because it's the element that actually does the voltage boosting. An inductor resists sudden changes in current, and it stores energy in its magnetic field whenever current flows through it. In a boost converter, this inductor gets charged up with energy during one part of the switching cycle, and then releases that stored energy into the output during the other part. The back and forth of charging and discharging this inductor, many thousands of times per second, is what allows the output voltage to end up higher than the input voltage. Right after the inductor is the switch, drawn here as an IGBT, which stands for Insulated Gate Bipolar Transistor. This component behaves like an extremely fast on and off switch. Its gate terminal is driven directly by the PWM signal coming in from port 1, labeled PWM. That PWM signal is exactly the switching waveform generated by the control blocks we covered in earlier videos. When the PWM signal turns the switch on, it creates a direct path from the inductor down to the negative rail, essentially short-circuiting that point in the circuit to ground. When the PWM signal turns the switch off, that path is cut, and the inductor is forced to push its stored current somewhere else. That somewhere else is exactly where the boosting effect comes from, and we'll walk through that in detail in the next section. There's also a diode drawn inside the same symbol, in parallel with the switch. This is a built-in freewheeling diode, and it protects the switch by giving any unexpected reverse current a safe path to flow, rather than damaging the switch itself. Let's walk through the two states of a full switching cycle. State 1. The switch is turned on. Current from the input flows through the inductor and then straight through the now closed switch to the negative rail. During this time, the inductor is charging up, storing energy in its magnetic field. Because the switch provides a direct low-resistance path, the output diode is naturally blocked and the load current at the output is being supplied only by the output capacitor. State 2. The switch turns off. Now the inductor's stored energy has nowhere else to go except forward, through the diode, into the output. Because an inductor always resists sudden changes in current, it responds to being suddenly cut off by dramatically increasing its voltage, pushing current out at a higher voltage than the input. That higher voltage pulls charges up the output capacitor and supplies the load. Switch this back and forth thousands of times per second, and the result is a stable, higher direct current output voltage, built from the input voltage plus the energy repeatedly pumped through the inductor. Just after the switch and inductor junction sits a diode. Its job is simple but essential. It only allows current to flow one direction, from the inductor toward the output. This prevents the output capacitor from discharging backward through the switch whenever the switch turns on. Without this diode, all the energy stored in the output capacitor would simply drain straight back through the switch every single cycle, and the converter would never be able to maintain a boosted output voltage. On the output side, we have capacitor C1 connected directly across the out plus and out minus terminals. This capacitor smooths out the pulsing energy delivered by the inductor and diode into a clean, steady direct current voltage. Without it, the output would be a series of voltage spikes rather than a usable, stable supply. This smooth voltage is exactly what gets passed along to the rest of the system, whether that's a battery converter, an inverter, or any other downstream stage. There's one key mathematical relationship that governs this whole circuit. In an ideal boost converter, the output voltage equals the input voltage divided by the quantity 1 minus the duty cycle. The duty cycle is simply the fraction of each switching period that the switch spends turned on. What that relationship tells us is intuitive once you see it. The higher the duty cycle, meaning the longer the switch stays on relative to off, the higher the boost ratio, and the higher the output voltage climbs above the input. This is exactly the lever that the PWM signal, generated by the control loop we covered earlier, is pulling every single switching cycle, continuously adjusting the duty cycle to hit whatever target voltage the system needs. This block is the voltage brain of the inverter. It takes in a measured three-phase voltage and a reference voltage, and it outputs two things: a modulation index and a full set of three reference voltage waveforms. Together, those two outputs tell the inverter's switching stage exactly what voltage to produce, moment by moment. Inside, this function is running a complete DQ frame voltage controller. That's the same core technique used in real grid-tied inverters, motor drives, and power converters everywhere. In this video, we're going to walk through exactly how it works, one section at a time. Let's start at the top. Three constants are defined right away. Frequency is set to 50, meaning this inverter is synchronized to a 50 Hz grid. Phase is set to 0, meaning there's no artificial phase shift being added. And the sample time, TS, is set to 5 microseconds, which matches the discrete solver step used everywhere else in this model. Then we hit three persistent variables, T, integral VD, and integral VQ. Persistent means these values are remembered from one time step to the next, instead of resetting every time the function runs. Think of them as the block's memory. The variable T acts as an internal clock, and the two integral variables are the running totals inside the controller's integral term, which we'll get to shortly. Now the function builds its own rotating phase angle, completely from scratch, without using any built-in sine wave block. It takes the internal clock t, multiplies it by 2 pi and the frequency, and that gives a continuously increasing angle. A modulus operation wraps that angle back into the range of 0 to 2 pi, so it behaves just like a repeating sine wave cycle. From that angle, the function computes both the sine and the cosine. These two values are the foundation for everything that follows, because they define the rotating reference frame the whole controller operates in. At the very end of this section, the clock t is incremented by 1 sample time, so the next time this function runs, the angle has moved forward exactly 1 time step. Here's where things get interesting. The three measured phase voltages VA, VB, and VC get combined using sine and cosine terms shifted by 120 degrees from each other. This is called the Park transform, and it converts three sinusoidal signals that are constantly changing in time into two values, VD measured and VQ measured, that stay essentially constant when the system is balanced and running smoothly. Why does that matter? Because constant values are dramatically easier to control than moving sine waves. Instead of chasing a target that's always changing shape, the controller now just has to drive two steady numbers toward two steady targets. That's the entire reason this transform exists. Now, the controller compares those measured values against their targets. The D-axis target comes directly from the reference voltage input into this block. The Q-axis target is deliberately set to 0. That's an intentional design choice. By forcing the Q-axis to hold at 0, the controller focuses entirely on regulating voltage magnitude along a single axis, which simplifies the whole control problem. The difference between target and measured gives two error signals, error VD and error VQ. Each error feeds into a proportional integral controller, commonly called a PI controller. The proportional part reacts instantly to the current error. The integral part accumulates error over time, which helps eliminate any small steady offset that a proportional term alone would leave behind. Notice that this integral isn't built using a Simulink integrator block. It's written out by hand. The running total gets increased by the integral gain, times the error, times the sample time, every single step. This is sometimes called forward Euler integration, and writing it manually like this makes the code safe to convert directly into embedded C code without depending on any Simulink-specific block behavior. Right after that, there's a safety clamp. If the integral term grows past 100 in either direction, it gets forced back to exactly 100 or negative 100. This is called anti-wind-up protection. Without it, if the error stayed non-zero for too long, the integral could grow without any limit, and the controller would badly overshoot once conditions finally changed. Clamping it keeps the whole loop stable and well-behaved. Finally, the controller output for each axis is just the proportional term added to the clamped integral term. These two outputs, VD inverter and VQ inverter, represent the corrected voltage command in the rotating frame. The first output of this whole function is called M, the modulation index. It's calculated as the square root of VD inverter squared plus VQ inverter squared. If you think of VD and VQ as two perpendicular sides of a right triangle, M is simply the length of the hypotenuse. It represents the overall size of the voltage command, independent of its angle. This single number tells the inverter's switching stage how large the output voltage waveform needs to be. The second output takes those same two rotating frame values, VD inverter and VQ inverter, and converts them back into three separate phase voltages, again using sine and cosine terms shifted by 120 degrees. This is the inverse of the transform we used earlier, so naturally it's called the inverse Park transform. The result is three properly phase-shifted sinusoidal reference voltages, one for each phase, bundled together as the output called VABC inverter. These are exactly the reference waveforms the inverter's pulse width modulation stage needs in order to synthesize a real three-phase output. Stepping back out to the full diagram, the three-phase reference voltage feeds into a block that appears to select or process a single reference signal called Uref. That signal then passes through a one-sample delay, shown as 1 over Z, before finally becoming the PWM output that drives the switching stage. The modulation index, M, appears on the left side of this block as well, And while it isn't clearly wired onward in this particular view, it would typically be used elsewhere to help size the amplitude of the switching reference or to monitor how hard the inverter is working. Every grid-connected inverter needs to know two numbers at every single instant: how much real power it's delivering and how much reactive power it's exchanging with the grid. This block computes exactly those two numbers directly from the three-phase voltage and current measurements, using nothing but multiplications, additions, and one simple scaling constant. In this video, we're going to walk through both equations this block is built from and trace exactly how the diagram implements each one. Let's get into it. The block itself tells us exactly what it's calculating, right at the top. Equation 1. Real power, P, equals VA times IA plus VB times IB plus VC times IC. In other words, multiply each phase's voltage by that same phase's current and add the three results together. This is the standard formula for instantaneous three-phase real power, sometimes called active power, and it represents the actual usable power being delivered to or from the grid. Equation 2. Reactive power, Q, equals 1 over the square root of 3, multiplied by the quantity VBC times IA plus VCA times IB plus VAB times IC. Here, VBC means the voltage difference between phase B and phase C, VCA means the difference between phase C and phase A, and VAB means the difference between phase A and phase B. This formula estimates reactive power, meaning the portion of power that oscillates back and forth between the source and the load without doing any real work. There's an important note attached to this second equation. It's only valid for a balanced, harmonic-free system. That means all three phases need to have equal magnitude and be evenly spaced apart, with no significant distorted waveform content. If the grid connection becomes unbalanced or distorted, this particular simplified formula for reactive power will start to introduce error. The block takes exactly two inputs. Port 1, labeled VABC, is the three-phase voltage measurement, bundled together as a single three-element signal. Port 2, labeled IABC, is the three-phase current measurement, also bundled as three elements. These are the same voltage and current signals measured right at the inverter's output terminals, feeding directly into this block for power calculation. Let's trace the top path first, which computes real power. Both VABC and IABC feed into a multiply block. Because both signals carry three elements each, this multiply happens element by element. VA times IA, VB times IB, and VC times IC, all computed simultaneously as a three-element result. That three-element result then flows into a summation block, which adds all three products together into one single number. That single number is exactly equation 1 from the top of the diagram. P equals VA times IA plus VB times IB plus VC times IC. This output is labeled P, and it flows straight across to the final output multiplexer. Now, let's trace the bottom path, which computes reactive power. First, the three-phase voltage signal gets split apart into its three individual components using a demultiplexer. Once split, those three voltage values feed into three separate addition and subtraction blocks, arranged to compute the phase-to-phase, or line-to-line, voltage differences. The first block computes VB minus VC, giving us VBC. The second computes VC minus VA, giving us VCA. The third computes VA minus VB, giving us VAB. These three line-to-line voltage differences are exactly the VBC, VCA, and VAB terms that appeared inside equation 2. Those three individual line-to-line voltage differences then get bundled back together into a single three-element signal using a multiplexer. That bundled signal is multiplied, element by element, against the original three-phase current signal, IABC. This produces three products: VBC times IA, VCA times IB, and VAB times IC, exactly matching the three terms inside the parentheses of equation 2. Those three products flow into a summation block, adding them all together into one number. At this point, we have the full expression inside the parentheses of equation 2. The very last step multiplies that sum by a fixed gain, 1 over the square root of 3, which is approximately 0.577. That constant comes directly from the mathematics of the three-phase power transform, and applying it produces the final reactive power value, labeled Q. Finally, both computed values, P and Q, get bundled together into a single two-element output signal using one last multiplexer. That combined signal is what leaves the block through the single output port labeled PQ, anywhere downstream in the model that needs to monitor or react to real and reactive power, whether that's a display, a logging scope, or a grid support control algorithm, simply taps into this one PQ signal. This scope is showing us 4 different signals from the simulation, stacked on top of each other, all sharing the same time axis running from 0 to about 0.6 of a second. Before we look at each trace individually, notice the one thing they all have in common. Every single signal is doing something different before the 1/10 of a second mark, and then settling into a steady, repeating pattern after it. That dividing line, right around t equals 0.1 seconds, is where the system finishes starting up and reaches its normal operating condition. Let's go through each panel one at a time. The top trace sits in a fairly narrow band between about 21 and 23 on the vertical axis. At the very start of the simulation, it begins near its highest value, around 23, and holds almost flat for a moment before curving downward. Then, right around the 1/10 of a second mark, it drops fairly sharply down to about 21.7, and from that point onward, it never settles into a clean flat line. Instead, it sits at that lower level but with a dense, continuous high-frequency noise riding on top of it for the rest of the simulation. Given the scale of this signal and the way it behaves, starting high, dropping once the system finishes its startup ramp, and then carrying constant high-frequency ripple, this looks very much like the array's output current. Early in the simulation, before the voltage has ramped up to its operating point, the array is sitting closer to a short-circuit-like condition, which naturally produces a higher current. As the voltage climbs during startup, the current settles down to its normal operating value, and the continuous fuzzy noise afterward is the electrical ripple caused by the switching action of the power converter feeding on this same current path. The second trace tells a very clean story. It starts at 0 and rises in a perfectly straight line, climbing steadily until it reaches about 260 around the 1/10 of a second mark. From there, it flattens out almost completely, holding right around that 260 level for the rest of the simulation, with only the faintest trace of ripple visible if you look closely. This straight line ramp up to a steady plateau is a classic soft start behavior. Rather than snapping the system's voltage up to its full operating value instantly, which could cause a large current spike or stress the components, the control system ramps the voltage up gradually over that first 1/10 of a second, then holds it steady once the target is reached. Given its scale, in the hundreds of volts, this is most likely the array's operating voltage, ramping up to the point the maximum power point tracking controller has settled on as the best operating voltage for the current conditions. The third trace is the most visually busy of the 4. It starts near 0, rises with a series of oscillations that grow larger and larger. You can see the swings getting wider as the trace climbs, and by the time it reaches the 1/10 of a second mark, it's settled into a sustained, regular oscillation, bouncing repeatedly between roughly 4,500 and 5,500, centered around 5,000. This shape makes a lot of sense if you think about what happens when you multiply the first 2 signals together. Power is voltage times current, and both of those signals were doing their own settling and oscillating during that same startup window. Multiplying a ramping voltage by a current that's also changing produces exactly this kind of growing oscillation during startup, followed by a steady ripple once both underlying signals have reached their own steady states. So this trace is very likely the instantaneous output power of the array, complete with the switching ripple inherited from the voltage and current it's built from. The fourth and final trace looks, at first glance, a lot like the second one, a smooth, straight-line ramp from 0 up to a steady plateau, this time settling around 5,800. But notice the scale. This one shares the same vertical range as the power trace above it, not the voltage trace. And critically, This trace has no visible ripple at all. It's a perfectly smooth line both during the ramp and after it flattens out. Putting those two observations together, this looks like a reference or filtered version of the power trace right above it, the target power level the system is aiming for, or a smoothed average with the switching ripple removed. It settles at a slightly higher value than the average of the noisy power trace above it, which is consistent with it representing a clean set point rather than the actual ripple-affected measurement. So, reading all four traces together, in the first tenth of a second, the system is starting up, voltage ramping smoothly toward its target, current settling down from an initially high value, and power climbing with growing oscillations as both of those settle. After that startup window, the system reaches a steady operating condition, a fixed voltage, a fixed average current, and a power level that oscillates around 5,000 due to switching ripple, tracking closely underneath a smoother reference power level just above 6,000. This kind of behavior, a clean startup transient followed by a steady, ripple-carrying operating point, is exactly what you'd expect from a maximum power point tracking system settling onto its target after the simulation begins, with the switching ripple you'd expect from any converter-based power electronics running continuously afterward. We've now gone through this entire system piece by piece, so let's finish by pulling all the way back out and looking at the whole thing together, from the sunlight hitting the panel to the power leaving the inverter and reaching the load. Every block we're about to walk through has already been covered in detail earlier in this series. This is the map that ties all of it together. Everything starts here, at the PVG block. This is the solar array itself, modeled from first principles using the single diode equation. Inside, one function calculates the photocurrent generated directly by sunlight, based on irradiance and temperature. A second function calculates the diode current lost internally to the cell's own PN junction, which depends on temperature, the array's operating voltage, and its operating current. Those two currents are combined and pushed through an actual physical circuit, a controlled current source, a series resistance, and a current sensor whose reading feeds right back into the diode calculation. The result is a block that behaves exactly like a real solar panel, producing more or less current depending on how much sunlight and heat it's given and how hard the rest of the circuit is pulling on it. The array's voltage doesn't sit at a fixed point. There's one specific voltage where the panel produces maximum power, and that point drifts as conditions change. The perturb and observe block is constantly hunting for that point. Every simulation step, it checks whether the last small nudge in voltage increased or decreased power, and it either repeats that nudge or reverses it. Over many steps, this walks the operating voltage toward whatever value is currently producing the most power. That target voltage gets handed to the PWM generator, which compares it against the array's actual measured voltage, runs the error through a PID controller, clips the result to a safe range, and finally compares it against a fast sawtooth carrier wave to produce an actual switching pulse train. That pulse train drives the boost converter's switch directly. The boost converter takes the array's raw voltage and steps it up to whatever level the rest of the system needs on the DC bus. Its switch is being told exactly how long to stay on or off by that PWM signal we just described, and the resulting duty cycle is what forces the array's actual voltage to lock onto the maximum power point voltage commanded by the tracking algorithm. This is the block that turns the tracking decision into physical reality. Sitting alongside the solar side of the system is the battery. It's modeled as a lithium-ion pack built from series and parallel strings to reach its rated voltage and capacity, with a full discharge characteristic, cutoff voltage, internal resistance, and the characteristic exponential then flat then dropping voltage curve that real lithium-ion cells produce as they discharge. This block state of charge is what everything else in the battery system reacts to. This is the energy management system, and it's the decision maker for the whole battery. It continuously compares how much power the solar array is producing against how much the load is demanding, and it checks the battery's current state of charge against safe upper and lower limits. Based on that comparison, it decides whether the battery should discharge to cover a shortfall, charge to absorb a surplus, hold steady because supply and demand are balanced, or fall back to a protective reference because the state of charge has hit its limit. Whatever power level it decides on gets compared against the battery's actual measured power, and that error drives a PI controller, which gets clipped by a saturation block and converted into a switching pulse train the same way the boost converter's PWM was built, by comparing against a sawtooth carrier. That pulse train, and its exact logical opposite produced by a NOT gate, become the two gating signals for the battery's power converter. These two switches form a bidirectional half-bridge between the battery and the DC bus, and together they are what physically execute the energy management system's decision. When the battery needs to discharge, the upper switch operates in boost mode, stepping the battery's voltage up to feed the bus. When the battery needs to charge, the lower switch operates in buck mode, stepping the bus voltage down into the battery. Same hardware, two directions, both driven by the same power decision from the control block. By this point, both the solar side and the battery side have contributed to a single shared DC bus. This gray bridge is where that DC power finally becomes AC. It's a three-phase switching bridge, and its gating signals are what actually shape the output into a usable waveform, based on the modulation index and voltage command coming from the inverter's own controller. So, start to finish, sunlight and heat drive the solar array, a tracking algorithm and boost converter pull the maximum possible power out of it, a battery and its own control system fill in whatever gap exists between generation and demand, a three-phase inverter and its own voltage controller turn all of that combined DC power into clean AC, and a final filter and measurement stage deliver it to the load while keeping tabs on exactly how much real and reactive power is flowing. Every block in this diagram exists to serve one of those jobs, and every equation we've walked through across the series was really just the mathematical description of how each piece decides what to do next. That's the complete system, beginning to end. Thank you for following along through this whole series. If there's a specific block you'd like revisited in more depth, or a different operating scenario you'd like to see simulated, let me know in the comments. See you in the next one.